This is my colleague George Djorgovski, a professor of astronomy here at Caltech. George has worked on numerous areas in observational astronomy, spanning physical sources like galaxy formation, globular clusters, gravitational lenses, quasars, gamma ray bursts, various cosmological tests. George is well known, though, because he was one of the first astronomers to recognize the promise of combining large sky surveys with computationally sophisticated methods. And George was one of the founders of the so-called Virtual Observatory, as well as the Center for Data-Driven Discovery here at Caltech. George's talk will be on the astronomy data landscape and observable parameter spaces. Let's welcome George.
Thank you. Thank you, Andrew. Well, good morning, everybody. So the purpose of these short course talks is to educate each other and to tell people who are not experts in a particular field what's going on. So those of you who are savvy with big data astronomy will not learn anything new from this. But the others hopefully will. And my point is that we're actually much further along in terms of big data and the analytics than most people realize if they're not already working in the field. So what I'll first do, I'll put this in a little broader context of our information revolution and big data. And then I'll talk about how astronomers have dealt with this so far and just how much data do we have. Then I'll tell you a little bit about how we analyze these data using machine learning and things like that, but not in any great detail because you will learn about that in much more detail from a much more knowledgeable expert that comes after me. So in general, we find that in just about every field and every domain, there is now an exponential growth of data volumes, and it follows roughly Moore's law for the same reason that devices that generate the data follow Moore's law, meaning data double roughly every year and a half, which means, think about what that means. That means that next year and a half we generate as much data as in all of the past history. And our understanding doesn't double every year and a half. Now, the more interesting parts to this, I think, is that not just the data volume, but data quality and data complexity, information content also grow, although not exponentially. So there is a number of consequences of this that are changing the way we do science, as well as anything else, that we transitioned from data poverty to data glut. The data used to be coin of the realm. If you want to do science, you have to have data. Now, data are more or less a curse because it's a little bit like inflation in money. If your government prints a lot of money, money is not worth very much. What is valuable, however, is the expertise and creativity as to what to do with these data. And since the growth is exponential, that means that basically every data set becomes data stream. And you'd like to go through data only once if you can help it. The era of you gather data in a data set and then analyze at leisure is pretty much going away because you'll never catch up. So we're moving into the real-time analysis and discovery. And also, there are so many data sources that you can never centralize this. That's why Virtual Observatory came about. So the question that sometimes is asked is why is not this same old stuff just with more data? And there are three things that I can think about it. The first one is that for the first time in history, we're not able to see all of our data. There's just too much of it for human bandwidth. And so we have to have technologies that will take care of that for us. The second one is this increased information content that we now have what is called data-driven science as opposed to traditional hypothesis-driven science. I'll comment on this in a moment. And the third and the most interesting one to me is that we're pretty sure that in data sets of complexity we're getting now, there's meaningful structures, phenomena, that are simply incomprehensible to humans without some kind of aid like machine intelligence. Another way that's phrased is due to my late great friend of Jim Gray, that's him in the last row, who noted that science seemed to have progressed in different stages. It started with experimental science from ancient Greeks, but let's say Galileo. And then analytical theory from Newton's days onward, and both of those are still the mainstays. And in the mid-20th century, we started using computers for number crunching. That's called the third or von Neumann paradigm. And we still do that. But starting in about 1990s, a different kind of computing came about, the data-driven computing. And if you think about it, most of the time, when you're using computer, you're not doing any computing. You're using it to discover and access and modify some kind of information. So the growth of data then opens up new possibilities for discovery and requires different types of computational architecture and knowledge and so on. So this is a crude attempt to summarize what's the difference between traditional hypothesis-driven science and data-driven science. They're really very similar. Traditionally, you have some idea, design an experiment, get some data, analyze it, you understand what's going on. And of course, there are feedback loops along every step of the way. But now we generate so much data, usually for some purpose, but it can serve many other purposes which people who took the data never thought about. In other words, we do not observe phenomenology of physical world, we observe data. Parts of phenomenology are captured in these rich data sets. And let data suggest to us what's inside the data, like correlations, clusters, whatever. Then we can form hypotheses. Where does this observed data phenomenon come from? And so on, and then it becomes pretty much the same thing. So astronomy has been on the forefront of these developments for a long time. And astronomers like to always use the latest technology to get most out of the light that comes from the sky. In 1980s, we started having first proper digital imaging arrays, and so astronomers started doing image processing. By about 90s, we were getting gigabytes of data, and then we started getting into digital sky surveys, into terabyte regime from, say, early 90s into 2000s, which is when the virtual observatory framework was coined together in order to cope with exponential data flood. Now we're in a petabyte regime, and we're developing the hybrid field of astroinformatics, which is just like bioinformatics or geoinformatics. It's a data science as applied to astronomy. And we're streaming into the exabyte regime with future large surveys. So at every stage of this, we had to introduce new type of tools to go from data into knowledge. And most of the challenges are not from the data volume or data rate, but from data complexity and heterogeneity and things like that. OK, how much data is there in astronomy? Turns out nobody knows, even people whose job is probably to know such things. So I looked into some chicken entrails, and I came up with my best guess for today, that in terms of actually nice, curated, findable data, there's maybe about 200 petabytes, give or take factor of 2 in the world. And it grows exponentially. It'll be twice as much in a year and a half. And of all the different astronomical instruments generate over 100 terabytes per day. Now, that's a lot of data. Most of it comes from sky surveys. So at the bottom, I give you some comparison. The human genome is less than a gigabyte. It's nothing. The human memory, I've seen estimates ranging by many orders of magnitude, but kind of geometrical mean is maybe a gigabyte. And I believe this. This is why we remember things that never happened, and vice versa. And if you look just at ASCII text, a terabyte is 2 million books. And the human ability to process information, well, again, depends what. But if it's text, it's much less than a terabyte per year. If it's images or videos, it's much more than a terabyte per year. But that would be, say, geometric mean. So this is why we have to have technology to help us go through all the data. Well, this is a beautiful picture, which is actually not an image at all. It's generated out of the catalog of data collected by the Gaia satellites for about 2 billion stars, just putting down dot of appropriate brightness in an image plane. And this is not even a full picture of the Milky Way. But now that we've done panoramic sky surveys on just about every frequency, we then do it again and again and again. And typically, these surveys find of the order of billion sources and measure hundreds, if not thousands, of parameters for each one of those, and then do it again. So now we've done this pretty much at every electromagnetic wavelength, and we're opening other regimes, cosmic rays, neutrinos, gravitational waves. So this is a picture of the same piece of sky seen in 4 wavelength bands, and it shows you how different sky looks in different parts of the electromagnetic spectrum, because different astrophysical phenomena contribute energy in different bands. So if you only confine yourself to one of those, you're getting a highly biased picture of what's going on, and we're driven into the panchromatic view, and now with the synoptic sky survey into synoptic view along the time axis. So here is just a quick sampler lifted from a paper by Zhang of how things increased in time. The first digital sky survey I was involved in is digital second Palomar sky survey, is whole 3 terabytes worth of pixels. And that was scary back in the early 90s. And then 2MASS, House.IPAC came along, and Green Bank, and so on. Galaxy, the satellite, created whole 30 terabytes. Sloan Digital Sky Survey is probably the best known of them all. And the latest data release has 170 terabytes worth of data in it. Now, SkyMapper has promised 500 terabytes, but we'll see. And Pan-STARRS is delivering on schedule multi-petabyte data set. And of course, future surveys like LSST will exceed that. We're now at the point, it's indicated on the right, the Zwicky Transient Facility that generates approximately 1 petabyte per year. And that's roughly 1/10 of what LSST will do. So here are some of the local producers of this data, just to give you an indication and show you the evolution of it. What was really last generation sky survey, Catalina real-time transient survey that we've done, generated about 100 terabytes of data to date. Currently generates 25 terabytes per year. It was much less in the past. Zwicky Transient Facility for a 3-year survey will generate a little over 3 petabytes of all data products, and now gets about 1 terabyte per night just worth of images. But then, of course, we never reduce data in volume. We make it more. So it's maybe 4 terabytes per night worth of all data products. And radio astronomers are going to put us to shame. And just local experiment, Greg Hallian's part of long wavelength array at Observatory, collects 12 petabytes of raw data per day, but archives only 50 terabytes per day, because most of the bits really never leave receivers. So it adds to about 18 petabytes per year. Its Australian counterpart, the Murchison, I forget what W is for, array, is a little less than that, but comparable to that. The other experiment at Observatory, the assay will produce a little less, but to archive even less, but it's just a different purpose for it. Now, space missions actually are not major data generators, and the reason for this is the bandwidth. It's really hard to transfer a lot of data from the orbit down to the archives and analysis on the ground. So Kepler, with all of the fantastic science that's done, is only like 20 terabytes, I think. Galaxy, which did full-blown ultraviolet sky survey on the sky with multiple passes, 30 terabytes. And Gaia, which is the latest, bestest we have out there, for 5 years is expected to deliver 200 terabytes. So in comparison to the ground-based stuff, space does not contribute much, but it's really interesting, high-quality data. I've stolen this slide from Matthew Graham. I think he might show it also, just to show you what Zwicky Transient Facility, our synoptic sky survey, is doing now. That's building on earlier surveys at Palomar, Palomar Transient Factory, Palomar Quest, CRTS also in this building. And so the numbers are pretty impressive. These slides will be also online if you want to look at them. So Zwicky Transient Facility is now acknowledged to be a real precursor to LSST. It's about 10% of LSST. And if you look at data volumes of digital sky surveys we've been involved in for the past 15 years, they all sit right on the Moore's Law curve. So circa the turn of the millennium, astronomical community realized we have a challenge here, and this is where virtual observatory framework came from. The idea was to have a complete framework for astronomy with massive complex data sets, like one-stop shopping that scientists can just sit at their computer, access all of the data, tools, and so on. Up until then, we had this archipelago of disjoint archives from different space missions, different observatories, different surveys. And it partly succeeded. It really became global data grid of astronomy, that essentially all of the astronomical data that are worth using for anything today, unless they're protected by 18-month proprietary period, are all accessible online to anybody in the world with an internet connection. And I think astronomy may be the only science that can boast of something like that. So that's a really powerful enabling role. So this is coordinated more or less by an international organization called International Virtual Observatory Alliance. And I have mixed feelings about it. Sometimes I compare them to United Nations of Astronomy, but not nearly as efficient. But they do have one web page that is pretty good. There lists and links all manner of useful tools that people have developed, whether through VO projects or otherwise. And otherwise, it's just a standards coordination body. Now, that became sort of global data grid. What about science? This is where astroinformatics comes from. The foundational conference of the field was right in this auditorium 10 years ago. Oh, sorry, 9 years ago. And it's just like bioinformatics or other X-informatics. It's the bridge amalgam field of data science and a domain science like astronomy. And it aspires to include much broader community as both users and contributors to it. Now, it's just like other data science fields, it's a composite. It's got many parts in it, from data farming to data analytics and everything in between. And data analytics itself has many parts to it, including machine learning, statistics, and whatnot. And I'll point out that the 10th annual Global Astroinformatics Conference will be here, in fact, in this very room, June 24 through 27 this year. So do come. So this is sort of cartoon version of how astronomy is done now in the era of big surveys. You get some kind of surveying telescopes. They're usually small, whether they're in ground or space. These are Ocean-Schmidt, Palomar, and WISE satellite. And then there's a pipeline that converts raw data and calibrates them and then does image segmentation, finds objects, and measures many parameters for each one of them and feeds them into some kind of database in an archive for that particular survey or mission. And there are many, many of those. So these archive catalogs of many different properties of sources represent feature spaces in which we can do stuff. And you do the analysis, you find things of interest, whether things that you know you're looking for, or maybe things that are surprising and so on. And then you turn the big guns on it, telescopes on the ground or space, to actually learn what's going on, typically by taking a spectrum or so on. So this is simplified, but that's the basic idea. So essentially, astronomy today, almost all of the real action is in data analytics systems. All of the expensive hardware that gathers the data is just the front end. All the action is really in the computer. And it's only going to get more so. So the stuff that we're telling you about today, about how do you extract knowledge from these vast data sets, is actually something that's really useful. This totally satisfies Dyson's law of utility of data. In fact, I'm not talking about SETI at all. Everything I'm telling you is what we use now to make new discoveries in astrophysics. So most of the stuff really can be put as exploration of parameter spaces. And that can be different kinds of things, looking for clusters and correlations and anomalies and outliers and gaps and whatnot. And there are many different types of tools and algorithms and models and so on. And usually, they don't scale very well with dimensionality of the data. Moore's law takes care of the number of data vectors, but not their dimensionality. And so generic problem of data science then is something like this, that you have some huge data space, many, many dimensions. Each thing that you're measuring is one dimension of the data space. And this is my flat cartoon of a 3D representation of, say, 3,000 dimensional data space. And data fill it up in some manner, but not uniformly, and not according to any simple statistics. And they're missing data, and they're heterogeneous data. And most of the stuff is actually not interesting at all. Most of the things that we measure have no utility whatsoever, but you don't know a priori which ones. And so somewhere in these huge data spaces, there are subsets of dimensions, subsets of regions in which something interesting is happening, correlations or clusters or what have you. And so that's essentially a generic problem, and it cannot be done through brute force because of the scaling and limitations of the hardware. Okay, so back to astronomy. This was really initiated by our saint protector, Fritz Zwicky, who, among many other innovations, came up with this thing called a morphological box, which nobody understood. And today we think morphology is like butterfly collecting. But in modern lingo, this is what we would call parameter space. He said you look at all of the different properties of things in the sky, and then in each cell, region of this parameter space, which is not forbidden by the laws of physics, you look, is there something there? And you might find things that you never knew about. He, in fact, used this approach to discover compact starburst dwarfs, which then later were rediscovered by the Galaxy Zoo and called the green peas. He was like way ahead of his time and just didn't have the data to do this. By the way, he pioneered also sky surveys at Palomar. So a generic view of this is there are many kinds of things you can measure. And they're all axes of some observable parameter space. This is parameter space of observations, not objects. And each observation carves a hypervolume in terms of area, depth, wavelength coverage, resolution, whatever, right? And roughly speaking, there are things that have to do with spectrum, the photometry, things that have to do with motions, things have to do with structure on sky, and things have to do with temporal changes. And there are many axes in each one of those. So this is a way to compare different observations and different surveys. So we unleash some pipelines on this, and then we find sources, and we measure a bunch of things for them. And then sometimes those just measured quantities are interesting. Like this is on the left is 2D color space from Sloan Digital Sky Survey. Stars are the black points, and the missing regions is just there are too many black points to point. Colored ones are quasars. And so you can already do some interesting science with just observed quantities. But sometimes you want to convert those into physical quantities like masses and luminosities and physical sizes or what have you. And so you have to use some additional data to transfer from observables to physical properties. And interesting things can happen. You find that there are some multivariate correlations and so on. These are real data, by the way, of hot stellar systems. A familiar example to all of people who have taken Astronomy 1 and higher will be the HR diagram. You measure colors, the proxy for temperature, and magnitudes, which at a given distance are luminosity. And you find out that stars don't fill up this two-dimensional parameter space. They sit on these one-dimensional sequences, which wiggle around, and they each correspond to a particular stage of stellar evolution and nuclear reactions and so on. And sometimes you find outliers. You can see that in the left plot, the one called BS doesn't stand what you think for. It stands for blue stragglers. And those were typical outliers that they should not have been there. But turns out they are. And there are some interesting astronomical processes that put them there. But for example, we do not expect to find very low mass star that's superluminous. That just doesn't exist in nature. There are really good reasons why it doesn't exist in nature. But this is sort of an example. Now you fold other data like distances to stars, models of stellar evolution, and so this is how we get to analyze things and find stuff. So we have these big surveys, and we map them out. Generally speaking, objects of given physical type, like stars or galaxies or quasars or supernovae, they will occupy a particular region of the parameter space, not fill it up. And different objects will be in different clusters. So if we have enough training data sets, we can use this to automatically classify things, one of the basic parts of processing. But there is also a set of techniques that Kiri will talk about unsupervised clustering, that you do not assume anything about which objects populate your data space, but you let the data tell you what's in the data, how many different kinds of things are in the data. And some of those, then you may recognize, oh, that's stars, or that's quasars. But some of them, you say, oh, what's this? We don't have any examples of this. And so that's been the hope of essentially all digital sky surveys for the past 20 years, to find things in these rich new data spaces that we didn't know about before. Spoiler alert, we didn't find any. What we did find were rare examples of subtypes of interesting things like peculiar supernovae or peculiar quasars and stuff like that, but not a fundamentally new phenomena of nature. The only thing that kind of fits in that would be fast radio bursts, which are found in a completely different way. And so this is a generic thing. Normal things form some clusters. You define outliers. Sometimes you know what to expect because of prior knowledge. And this is a standard way in which quasars are found today. But sometimes a thing you didn't expect occupies the same portion of the parameter space. And we have understood what this was. It wasn't new, but there we go. So there are many, many, many of these tools, hundreds of them actually. And they're all useful for different things. Hopefully, Kiri will cover this in much more detail. But first, I talk about these outliers. So what's an outlier? Well, look at the histogram first. What's the underlying statistics? If you fit a Gaussian, then this thing on the extreme right does not belong. It's an outlier. But maybe you just have the wrong probability density function. And usually people assume that everything is Gaussian. And in real life, almost nothing is Gaussian. Fat tails are prevalent. This is why there are so many wrong 5 sigma results, because they're not Gaussian distributions, right? And sometimes it's kind of obvious, and sometimes it isn't, depending on what density function you assumed. Like, if it's nice and easy, like the one in the upper right, sure, you can tell what, you don't need machine learning, you just put circles around points. But if it's more like a blob in maybe multiple overlapping blobs, what's an outlier? And so definition of an outlier, potentially interesting object, really depends on what you assumed about distributions for normal objects, right? Or somebody once said, if you're looking for a needle in a haystack, you have to be really good at classifying hay, right? So time domain is a big fad area now, and Matthew Graham will talk about exploration of that. But that generates all manner of new axes of parameter space, some of which have to do with where you're looking and how often, and what's your cadence, which in Fourier space then translates into selection effects. And then you measure things, and they vary in some fashion, but you don't, usually we don't have these deluxe time series like in radio astronomy that are long and uniform and finely sampled. We have sparsely sampled, lousy, uneven time series and have to extract knowledge from them. So there are many parameters, over 70 that have been defined, and each of them would form an axis of parameter space. So how do you deal with heterogeneous data? Well, there's a trick. Instead of analyzing the data, you describe the data as a set of statistical descriptors of how they behave along the time axis. And now, for any light curve, regardless of the number of data points and the sampling and the gaps and so on, you have same set of features, uniform feature space, which you can use for machine learning. This is real data, by the way. Well, there are many of those. I will not explain them. Maybe Matthew will focus on some of those. But the point is that now we get this high dimensionality feature space of variability of things on the sky. And some are periodic, and some are not, and some only show up once, and so on and so forth. And so this is where a lot of action is today. Now, it turns out a lot of these algorithms scale really badly with the number of data dimensions. We're not looking 2 or 3, we're looking 30 or 300. And there is a premium in being able to eliminate those that are really not containing much information. So there are one set of algorithms called those are all called dimensionality reduction techniques. And one of them is feature selection algorithms using some sort of statistics and machine learning to figure out which of your many, many things are actually useful for whatever problem you're tackling. And you're tackling different problems. What are you trying to do? Are you trying to predict one variable as a function of many others? It's a regression problem. Or are you trying to classify one kind of thing versus another kind of thing, supernova versus non-supernova, or something like that, and so on. And each of those is optimized in a different way, and for each data set. So there is no one size fits all. You really have to kind of know what you're doing and explore the algorithms and their applicability. And there are a couple of papers there that I can direct you to. So I'll skip this over. And this is just to illustrate how this works. So on the top are the 2 light curves of 2 different variable stars, and they're very different physically. One is pulsating variable, the other one is eclipsing binary. And it'll be hard-pressed to tell what's going on just looking at the raw data. So you run one of these feature selection tools, and it sorts in the order of importance which ones will be the most useful for classification. And you take the top 3, and boom, it separates cleanly the 2 clusters of objects that you just will never be able to see otherwise. So it's validated by additional observations. So just then, we give you a couple examples of different types of unsupervised clustering studies done by others. There is one by Dalia Baron and Dovi Poznansky. They looked at spectra from Sloan Sky Survey, and then they parameterized spectra in some way, and then used, they defined an outlier parameter they call weirdness, and look for the weirdest galaxies in terms of the survey parameter space. And they didn't find anything new. They found lots of outliers, but they were able to interpret every single one of them as one kind of thing that we know, particular extreme case of this or that type of galaxy. Nevertheless, it was a good attempt. Here is another one by Rubin and Galliam. They looked at light curves of type 2 supernovae, and they found out that just by the shape of light curve, there seem to be 3 significant groups, which are shown in particular projection over in the lower right. And then types of them are indicated sort of in the thing on the left. They don't really look all that different. They're kind of continuum of changes, fast rising, slow decay, fast rising and fast decay, or something like that. So it's not clear that those are physically distinct subsets of objects or just simply different ends of a continuous distribution. Nevertheless, it was a good paper to look at. So here, to summarize that important points, that we're very much into petascale data regime now, and we're streaming toward exabytes. Most data are from large surveys, which are uniform. The biggest growth is the time domain, which covers sky again and again and again. And this is happening at all wavelengths that we can access. Now, the interesting part is not data volume. Data volume is interesting. You're looking for rare kinds of things, 1 in a billion. But data complexity, which can tell apart different types of objects. And we're fortunate that we can actually isolate sources in the sky and not just have a mushy distribution of signal. And then for each object that we detect, we measure hundreds, if not thousands, of different parameters which form feature spaces for machine learning to be used. And we've already been using machine learning since the early 1990s for different tasks involving this. And we have more and more interesting challenges for computer scientists like Kiri and Uma to help us with. So I'll stop at this point. Thank you.